x has exponential distribution with parameter lambda and b is given as this event taking the values between 1 to infinity. Now, we have to find the conditional probability density function. First, the conditional CDF, cumulative distribution function. The conditional cumulative distribution function is given by, so this is nothing but x given b, which is nothing but probability that x less than equal to x intersection b by probability of b. First, we have to find what is the probability of b. Now, x is as x is, since x has exponential random variable, we know what is the probability density function of x. So, the probability density function of x is given by, so that is why we discussed all this distribution first, because it is known to us, all are known to us, we need not to learn it again, just we already learned it. So, it is nothing but lambda e to the power of minus lambda x whenever x is greater than 0 less than infinity and 0 otherwise. So, this is the probability density function. So, probability of b, what is that? So, probability of b is nothing but probability that it is random variable taking values 1 to infinity. So, this is because b is 1 to infinity. So, this is nothing but 1 to infinity lambda e to the power of minus lambda x dx, because this is the probability density function, we are integrating over v. So, this is nothing but lambda e to the power of minus lambda x minus lambda if you take this integration, and this is 1 to infinity. So, then you can see that at infinity it is 0 and lambda cancelled, and at 1 it is nothing but e to the power of minus 1. So, this is nothing but 1 by e. So, probability of b we found. Now, what will be probability of x less than equal to x intersection b? So, probability of x less than equal to x intersection b. Now, note that x, so x is a positive random variable, it is taking only positive number. Now, x is actually positive random variable 0. Now, this is b is nothing but 1 to infinity. So, b is nothing but this set 1 to infinity, and x is any value. So, this will be is equal to 0 if x is less than 1, because whenever x is between 0 to 1, so this intersection is nothing but, we can just write in another step, this is nothing but x less than equal to x intersection 1 to infinity. So, that is why, so b is, it is given it is open interval 1 to infinity. So, that is why this is equal to 0 if x is, so if x is less than equal to 1 greater than 0. So, any value you can take, then there is this intersection is phi null set. So, then it will be 0. So, x is suppose 0.5 if you take. So, this is nothing but here, and this is the b is here. So, this intersection is phi. So, any value you can consider, this intersection will be x between 0 to 1, then this intersection is just a null set. So, that is why this probability will be 0. Now, if you now what will be the case when x is greater than 1 less than infinity? Whenever x is greater than 1 less than infinity, we can compute this value. So, basically x is here, somewhere here. So, here or here, x is greater than 1. So, basically what will be the intersection? So, this is equal to, whenever x is, this is nothing but this intersection is, suppose x is here, this is 1 to x and 1 to infinity. So, this is nothing but intersection of nothing but 0 to x, intersection of 0 to x intersection of 1 to infinity. So, this is nothing but 1 to x, this x is greater than 1. So, that is why this intersection is nothing but, this is nothing but the probability x less than equal to greater than equal to 1 less than equal to x less than equal to x. So, this probability is nothing but so whenever 1 less than x less than infinity, this probability is nothing but 1 to x. So, let us find out this probability first. I hope you have understood it. So, it is clear now, whenever x is greater than 1, this interval, this intersection will be nothing but 1 to, because it is 1 to infinity and is 0 to x, this intersection will be nothing but 1 to x. So, now we will find, just erase these things and then we will find out what will be the probability, this probability. So, this probability is nothing but, so probability that 1 less than equal to x less than equal to x, this probability is nothing but 1 to infinity, sorry, not 1 to x, 1 to x, then f x x dx. So, I just take different variable t dt. So, this is nothing but 1 to x, this is lambda e to the power of lambda t dt. So, this is nothing but lambda e to the power of minus lambda t by minus lambda, this integration by 1 to x. So, basically lambda cancel, this is e to the power of minus 1, they add minus, because it is there is a minus 1 here, that is why this will be just minus 1 minus e to the power of minus lambda x. So, 1 minute. So, I think t is equal, it is not just because there is a lambda here. So, it is lambda t, lambda into 1. So, this is e to the power of minus lambda, e to the power of minus lambda x. So, I think it is fine now. So, this is the probability. I just remember here I made the mistake. So, e to the power minus lambda x by minus lambda, x goes to infinity, this is 0, and x goes to 1, it will be e to the power of minus lambda, sorry. So, this is e to the power of minus lambda. So, this is the probability of B. So, finally, we will find what will be the conditional probability cumulative distribution function. Hence, so hence the conditional CDF is given by, so this is nothing but f x given b, x given b. What we found? So, we found that this is nothing but, so let us write down, so then it will be clear, probability that x less than equal to x intersection b by probability of b. Probability of b we have found. So, this is nothing but whenever x is less than equal to 1, sorry. So, we have found this probability is x is less than equal to 1, x is less than equal to 1. So, x is, so even if you take my negative number also, negative number it is always, it is 0, but whatever it is, any number it is 0. So, that is why we can write minus infinity, because you have to define whole real line. So, whenever x is minus infinity to up to 1, this probability is 0, already the upper part is 0, but whenever x is greater than 1 less than infinity, then probability b will be, probability b is nothing but e to the power of minus lambda, just now we checked it, probability of b is nothing but e to the power of minus lambda, e to the power of minus lambda. And what is the probability of this upper, so the upper part. So, this probability is, we just found it, this is nothing but same of this. So, this value is nothing but e to the power of minus lambda minus e to the power of minus lambda x. So, then e to the power of minus lambda, e to the power of minus lambda x. So, e to the power of minus lambda, e to the power of minus e to the power of minus lambda x. So, finally, what we got? So, this is nothing but this is 0 whenever x is less than equal to 1 minus infinity, and then just it is nothing but 1 minus e to the power of minus lambda into e to the power of minus lambda x minus 1. So, whenever x is greater than 1 less than infinity. So, this is the conditional probability distribution function for x given b. Now, in the question it is asked that what will be the conditional probability density function of x given b. So, now what we have to do? We have to just differentiate it with respect to this. So, the conditional probability density function of x given b is, so this is nothing but probability f of x given b x given b, it is nothing but differentiation from of the conditional probability distribution function given b. So, this is actually we can see that this distribution function is this is 0. So, this will be 0 only x greater than 1. So, this will be 0 whenever x is less than equal to 1, greater than minus infinity, Now, if you take the derivative with respect to x, this is nothing but e to the power of minus lambda. So, that is why it will be positive lambda e to the power of minus lambda x minus 1. So, this is the probability density function whenever x is greater than 1, less than infinity. So, this is the finally we found the conditional probability density function of x given b. So, this is one example how to find the conditional probability density function given a event b. So, now next we will discuss what will be the conditional probability mass function for this example whenever x is binomial distribution with np, b is equal to 1 to n, find the conditional probability mass function of x given b. Next we will discuss. Now, we will discuss the conditional probability mass function on example. So, conditional probability mass function for a given event b. So, here one example it is given, let x be a random variable which is binomial distribution with parameter n and p, and b it is the event it is 1, 2, 3 up to n. Find the conditional probability mass function of x given b. So, we already discussed conditional probability density function. So, you can remember that the conditional probability density function when we computed, we need to compute the first probability density distribution function, cumulative distribution function. First we find the cumulative distribution function, then we take the derivative of cumulative distribution function, and then we find the probability density function. Now, for discrete case, cumulative distribution function may not be differentiable for all x, and in that case we discuss the probability mass function. Here we will directly find the probability mass function, conditional probability mass function. So, recall that what is the conditional probability mass function for a given random variable. Conditional probability mass function it is given by, so the conditional probability mass function mass function PMF given conditional probability mass function of x of a random variable, of a discrete random variable, basically discrete random variable x given b is equal to 1 to n. So, here this b is given 1 to n. So, let us discuss for a first for any b, event b is given b is represented as px of b, xk given b, xk which is equal to probability that x is equal to xk intersection b by probability of b. Now, for this example, so this example x is, you can see the example, x is binomial np and b is 1, 2, 3 n. So, x having, in this example x has a binomial distribution with parameter n and p. So, n is a natural number and p is probability 0 to 1 we discussed when we discussed the binomial distribution. Now, how we can find, and b it is given like the set 1 to n. So, what is first we let us find out the what is the probability mass function of a binomial random variable. So, this is the probability mass function of binomial distribution, the probability mass function, the probability mass function of a of x, actually it is a binomial random variable, so we write of x is given by px of, so here it is taking some value x is equal to, range of x will be 0 to n because it is a binomial distribution. This is nothing but, because x is binomial np, ncx p to the power x 1 minus p to the power of 1 minus x, so n minus x whenever x is 0, 1 to n, this is equal to 0 otherwise. So, we know this probability mass function. Now, we use this formula to find, by this definition, to find the this probability mass function of, conditional probability mass function of x given b. So, now this conditional CDF, conditional PMF, the conditional PMF probability mass function of x is, so how we can find, so probability that x given b. So, now this xk here basically nothing but, what are the xk? Xk can be just x is equal to 0 to n. So, we just write x given b, this is nothing but probability that x is equal to small x intersection b by probability of b. First we will find what is probability of b. So, probability of b is nothing but summation of, so probability is nothing but, it can take some, it can take, b is nothing but, so b is, it is given 1 to n. So, probability of b is nothing but probability summation that, because it is a discrete random variable, it can take the value. So, x is equal to 1 to n, probability that x is equal to x. So, this is the probability of b, because it is union of probability of x equal to 1 plus probability of x equal to 2 plus probability of, sum of the probability of x equal to 1 plus probability of x equal to 2 plus probability of x equal to n. But because it is a binomial random variable, so we know that summation of probability that x is equal to x is equal to 0 to n, we have already shown also. This binomial, for binomial it is a probability mass function of a binomial random variable, this should be equal to 1. So, which implies probability that x equal to 1 to n, probability x is equal to x, this is equal to plus, actually this is nothing but probability that x is equal to 0 plus this is equal to 1, because it is x equal to 0 to n, it is probability of x equal to 0 plus the remaining sum x equal to 1 to n, probability x equal to x, this is equal to 1, which implies probability summation of x is equal to 1 to n, px x is equal to x, this is equal to 1 minus probability x is equal to 0. So, what is probability x equal to 0? So, px x equal to 0 can be just px of 0. So, this is nothing but nc0 p to the power of 0 1 minus p to the power of n minus 0. nc0 is nothing but 1 and this is p to the power 0 1. So, it is nothing but 1 minus p whole to the power n. So, let us denote this is nothing but q to the power n for simplicity, where q is equal to 1 minus p is equal to q to the power n, where q is equal to 1 minus p. So, this is nothing but 1 minus x to the power 0 is px 0 is q to the power n. So, this is nothing but q to the power n. So, this is not this is equal to 1 minus q to the power n. So, now probability of x is what we found, x is equal to 1 to n, probability of x equal to x. So, this is nothing but 1 minus q to the power n, where q is equal to, where q is equal to 1 minus of p. Now, we found this value 1 by p to the power b. Now, 1 by p probability of b we found. Now, we have to find what is x is equal to x intersection b. Now, b is we know that this is 1 to n, so nothing but probability of x is equal to x intersection 1 to n. So, note that x can be, because original the x is the binomial distribution, x can take the value 0 1 to n. So, this value, this intersection, this will be null set if x is equal to 0, because this 0 does not belongs to 1 to n. So, the b. So, this is equal to, this probability is 0 if x is equal to 0. Otherwise, what will be the probability? Otherwise, suppose any other x, suppose x is 1 or x is equal to 2, anything. So, this value will be subset of 1 to n, because this belongs to this is a superset of this. So, this is if any other value, if x belongs to this, the remaining value for any other x 1 to n, any other value, this is nothing but probability that x is equal to the x, because this is nothing but subset of this random variable. That probability of x equal to x we already know. So, probability of x equal to x, so that I will write here. So, let us, okay, next page we write that. So, hence probability that x is equal to x intersection b can be written as it is equal to 0 whenever x is equal to 0, and any other values also it is 0, but because x has non-zero probability at x, but this intersection is 0, and x whenever it is belongs to 1 to n. So, this probability is nothing but x is equal to x. So, this is we can write x 0 when x is equal to 0, and probability x equal to x already we know that this is the probability of the binomial random variable. It is written here NCX p to the power x 1 minus p n minus x. So, this is NCX p to the power x 1 minus p n minus x. So, that is whenever x is belongs to 1 to n. For any other value it is actually 0 otherwise. So, basically we can combine these things with this. So, basically this is equal to this value, if x is this is equal to 0, any other values of x. For any other values of x, this is equal to 0. So, now finally what the probability mass function, hence the conditional probability mass function, hence the conditional probability mass function of x given b each probability that x given b. So, x given b, this is equal to, so this is nothing but, so here we can write probability x equal to x intersection b by probability of b. So, this is non-zero when this is, so this is NCX p to the power x 1 minus p to the power of n minus x by probability of b is nothing but probability of b, what we found, probability of b will be 1 minus q to the power n. So, probability of b here we computed 1 minus q to the power n. So, this is 1 minus q to the power n whenever x is 1 to n, this is equal to 0 otherwise. So, this is equal to 0 otherwise. So, this is two example we discussed here using the conditional probability mass function to find the conditional probability mass function, one example, and another example we have already discussed, that is conditional probability density function. So, here we end the discussion of univariate random variable, Next more we will discuss later again whenever it will be required. So, some of the basic concept and some of the examples we have already discussed, some of the important distributions also we discussed, and their numerical examples we discussed. Now, we will discuss multivariate random variable. We will start with bivariate random variables.